First of all, thank you very much for the opportunity to be here. It's my first time in the Catalysis Hub, and I'd like to thank Richard for this because we met at the Royal Society at a more festive occasion, and I was giving a talk, and then he said it'd be nice if I could come and also give a talk here in the Catalysis Hub. And so today I will talk about electrocatalysis for a change, although there's been some talks with electrons before, but they also contain quite a lot of complicated biochemistry. So I'll just take the biochemistry out of this. And so I thought that before I will give you a bit of overview of my research interest and what we're doing in my group. And so I'm very interested in basically addressing, like all of us, this energy trilemma on, how do we develop all these sustainable energy technologies that we need for the future, yet we don't rely on scarce material, on high temperature processes, energy consumption, things like this, how we can actually do better for the future so we don't have a problem with the scarcity of the supply chain. Now, I am not going to talk about this, but I am most famous to date for this process of hydrothermal carbonization, which I kind of discovered by accident. And I think this is a good lesson for all the younger researchers here. So in my postdoc in Max Planck in Germany, my job was to take biomass and convert it into useful chemicals. And then to use my expertise from my PhD, which was more on separation science, to try to figure out how we could separate these biomass molecules, these ones here in particular, from an aqueous environment. So while I was starting doing this, taking various biomass precursors, lots of pure ones, but also real biomass, worked a lot with cellulose and glucose, I was getting these black precipitates at the bottom of my autoclave. And so rather than kind of doing my job, I started being fascinated about what is this black stuff, why does it form and how it is. And in fact, it kind of changed the course of my career because I realized that you could make some very dissolved carbon in water at only about 200 degrees, and you could actually shape and tune the morphology and the properties of these carbon materials. So I spent a lot of time understanding what they are, how they form, how you could shape them. I also discovered that you do this in water, so you get this black stuff. You have an aqueous phase. This aqueous phase contains all these valuable chemicals, but there's something else at the interface between these more carbon materials and the chemicals, which are known in the literature as this carbon dot. So we're also working on this and trying really to understand the fluorescence and the properties of such ill-defined materials, why they fluoresce, how you could tune the fluorescence. So just to give you a flavor, these are some of the morphologies that we can do with these carbon materials. So pretty much we can take a biomass precursor and turn it into a tailor-made carbon for a particular application. I work a lot on batteries. There you don't want a high surface area, we can do this. If you want a catalysis, depending on the process, we could make nice carbon conductive support in all shapes and forms. And we could also hybridize this with other inorganic nanoparticles within one-step process that I said happens under more mild conditions from biomass derivatives. So for example, these are some platinum nanoparticles supported on a glucose-derived carbon. It's a one-step process, take glucose, take a platinum chloride, throw them in an autoclave, and then glucose will reduce the platinum chloride to platinum nanoparticle that they deposit in the middle where you have a more hydrophobic core of this carbon materials with more hydrophilic groups on the side. You can combine this with templating, so you could put one platinum in the middle of each nanoparticle, or you could take, these are some tin oxide nanoparticles that you throw with glucose in a reactor, and you self-assemble this tin nanoxide with carbon in spheres, and all many other examples that I can give you. So it's very nice to make carbon and carbon hybrids. And this works only with the cellulosic fraction of lignin, because you have to go through the hydroxymethylfurfural, a polymerization, and a dehydration. It doesn't necessarily work with the lignin fraction of the biomass. And so, but we also want to use the lignin fraction. And so what we do with the lignin fraction is we take lignin, we learn how to work with pure craft lignin, organosolved lignin, ionosolved lignin, and we do this process of electrospinning, and we spin lignin into fibers, which then carbonize. So again, we've been working many years on this process, and we've learned how to make tailor-made, freestanding carbon paper-like. We could make it with micropores, with mesopores, with no pores, with aligned fibers. We've stacked fibers together to increase the density. We can tune mechanical properties versus electronic conductivity. As I said, we can align them in different directions. And normally we use this freestanding carbon mats in energy application, mostly batteries, to make structural electrodes that have no current collector. So we do all these carbon materials, and in terms of application in my group, we work on two directions. This was actually from my talk at the Royal Society on the green cat and green bat. So half of the group is green bat and half of the group is green cat. And obviously today I need to talk about more the green catalysis side of things. And so we normally use these materials as catalysts for a wide range of reactions. But today I'm not really going to talk about that. But just to say that we work a lot on the design of this single atom catalyst within carbon materials. So all of this can be derived from a biomass. We've learned this process where we can do this magnesium templating, and we do some nitrogen doping, magnesium coordinates to these nitrogens, and then we can exchange the magnesium for different metals. So we could have, in this case, it took us a long time, because when you make the single atom catalyst, you always get a mixture of phases, and it's quite difficult to get a single atom. But I think with this method, we can now be quite sure that we have the majority of sites as single atoms, so we can work a lot with iron as well as nickel. So I put here just some examples. So we use this iron coordinated to nitrogen in oxygen reduction reaction. This is a very recent paper where you see that we get a very decent oxygen reduction reaction performance. But what is nice when we compare this with literature, so we determine the number of active sites in the single atom catalyst by two methods, from mass power spectroscopy and using electrochemical technique, which is nitride stripping that reacts and poisons the iron sites, and then you can quantify the amount of iron sites. And then we quantify this by the total number of active sites that we determined by ICP-MS. And you could see here that actually this is our material, this TAP 900, that we get one of the most high or the highest active site utilization so far in the literature for this reaction, which is quite nice and impressive, because it's not only that you have a lot of this active site, it's how many of them are actually active, and this is more important. Now, of course, there are still issues with this catalyst, in particular their stability. I think that's the next big challenge that we need to solve in order to make this catalyst a commercial reality for fuel cells, because they work quite decent, almost as good as platinum, but they're not very stable. Now, it turned out we've been testing the single ion catalyst with iron and nickel also for CO2 reduction. I didn't want to talk about this. I just put it very last minute, this slide. But it turned out that actually when you use nickel at a single site, you don't make much of a hydrogen. You make a lot of CO, which is useful. I mean, it would be nicer if we could have C2 products. And so what we're doing now, we're taking this catalyst and we hybridize it with some copper oxide nanoparticles to see if we could actually make better products. There's still work in progress. We're working with modelers to really understand what's going on and what's the difference between nickel and iron. In fact, with iron, you get quite a lot of hydrogen evolution and much less CO than with nickel. So the metal makes a huge difference. However, today, I want to talk about process where you could take biomass and put it to an electrolyzer instead of putting water to an electrolyzer to make green hydrogen on one side and high-value chemicals on the other side. Before I do that, I want to give you a bit of the perspective of the UK on green hydrogen. I'm sure most of you are aware, but UK has super ambitious plans of 5 gigawatts production of low carbon hydrogen by 2030, which is around the corner. And most of this should come from renewable electricity and particularly farms. So overall, in the net zero report for the UK, it is envisaged that we will go from about 27 terawatt hour of hydrogen that we have today, and we will increase this 10 times to 270 terawatt hour, which is highly ambitious. And it's also envisaged that actually this hydrogen is going to be used across all the sectors of the economy to decarbonize industry, in particularly heating in buildings, but I'm not sure how that is going. At the moment, I think there's been some resistance there, and in particular transportation, but not necessarily our own cars, but more heavy-duty transportation, trains, shipping, and so on, and agriculture as well. So how do we make green hydrogen? Well, clearly by water electrolysis. And so there are different types of water electrolysis, and I've listed all of them here. One is the traditional alkaline electrolyzer that uses a liquid concentrated KOH and electrolyte. The one that everyone wants to work on and is the most efficient of all of them is proton exchange membrane electrolyzer, where basically, well, in all of this, you basically oxidize water to oxygen, and then the protons get transported to whatever membrane you have there to evolve hydrogen on the other side. So the PEM is the most desirable of all of them. We have the solid oxide electrolyzer that uses a ceramic oxygen 2- conductive electrolyte, and then we have the upcoming anion exchange electrolyzers where they use an OH conductive polymer electrolyte to do this. So these are the four technologies that we have. Now, if we take PEM, for example, which is the most efficient one, and we look in cross-section, well, you will see that you have a bimetallic plate, which is form of titanium, and then you have an iridium catalyst, and that is for the oxygen evolution. And so the oxygen evolution is the most important reaction. It happens under high oxidative potentials. It's quite corrosive. That's why you need a metallic titanium and an iridium oxide catalyst, which is about the only thing that is mildly stable in these reactions. And then you see the Nafion in between. Is there a pointer? Yes. Sorry. There's the Nafion membrane here. And then here is the hydrogen evolution side. So you have a platinum supported on carbon, and then you have a carbon transport layer because here you don't work under so negative potentials for this reaction. Now, if you look at the overall efficiency, we all know that water splitting happens around 1.23 electrovolts. Now, of course, you have some resistance here, and this is normally what is the potential of a cell. And the potential of the cell is to do the fact that you have quite a lot of overpotentials. And for hydrogen evolution, these are the potential steps here. So you see that you have mostly one intermediate. So you don't have so much overpotential here. With only 0.05 milligrams per square centimeter of platinum, you could nicely evolve hydrogen. The problem is more the oxygen evolution reaction. And you see here there are 4 intermediates, and you need a catalyst, first of all, to break the scaling linear relationships between all these intermediates, but also something that is stable. And iridium oxide is just about the only catalyst that is stable now, and you still need quite a lot of it. And as you know, iridium is expensive, and so that adds to the cost of the electrolyzer together with this bimetallic plate. So my idea is, instead of electrolyzing water, could we actually electrolyze something else? And so biomass offers many opportunities for this because it has protons. And so the advantage would be that if you would oxidize biomass instead of water at the anode here, you would make high-value chemicals while you would at the same time evolve hydrogen at the cathode. And the nice thing about biomass oxidation is that it happens at much lower potentials than water oxidation. Now, of course, it will depend on the catalyst and will depend on the precursor, but in principle, you could oxidize this at much lower potentials compared to water. So overall, the efficiency of the whole process would be better. And we have many opportunities for biomass and biomass oxidation. So I want to talk today about glycerol oxidation. So we started with glycerol, and the idea is to take glycerol and oxidize it to whatever we will get, surprise, surprise, and then evolve hydrogen at the cathode. Now on the glycerol electrooxidation. So you can have different pathways to oxidize glycerol. So of course you could have the CO so single CO to carbonyl oxidation. You could have carbonyl to an acid oxidation, or you could have carbon-carbon cleavages. So I listed all this reaction here in black, red, and blue. And so this is the overall reaction. As I said, doing this would be highly advantageous compared to water because you won't need iridium oxide to do this. So you lower the costs. However, you'd see that it's difficult. People use platinum ruthenium. I didn't use this. And you will maybe eliminate you will have a higher CO tolerance, you'll have lower over potential here. And you could also tune the selectivity of the glycerol oxidation to get the product that you want. So I want to present briefly this paper that's just been published by my wonderful postdoc called Hui Luo, who unfortunately left me to go to Ceres Power, but she has done a tremendous job. She might want to come back to academia, though, as she told me. So strongly recommend her. So now, if you look at glycerol oxidation and you take literature and compare it, this is our study on pure platinum. I mean, we didn't do pure platinum, but we also tested pure platinum. This is platinum done by copper, polycrystalline platinum, gold. And you see, as you go to more sustainable catalyst metal oxides, that your potential is increasing a lot, the potential at which you could actually activate this glycerol. And if you look at the selectivity, so for example, let's take nickel oxide versus platinum. Platinum is much better at making C-free products, which are more valuable. There's this tartanic acid that is apparently very valuable for a very niche but expensive market of cosmetics. It makes your skin glow and all of those nice things. So the question is, there is not much known on the glycerol oxidation. So we were wondering, why are these metal oxides so bad? And is platinum really so good? What is the selectivity here? So what we did, so as I said, I normally work with carbon, but here we've supported all this on carbon, but that's about it. We took platinum and nickel, and we did a solvothermal reaction, and we varied the amount of nickel that we put on this platinum catalyst. So we had platinum with less nickel, platinum with equal amount of nickel, and platinum with excess of lithium. And so the questions we wanted to answer, kind of inspired by the CO methanol oxidation and this bimetallic platinum ruthenium, was, will this be a bifunctional mechanism where in fact you could separately absorb the CO on one metallic side and the OH on metallic side? Or is it the electronic structure of platinum that is modified by this nickel, and then you change the absorption of these intermediates? And how does this work for glycerol? And so basically for glycerol, we wanted to understand how the absorption energy of the glycerol and the oxidized intermediate is changing depending on the surface, the absorption energy of the OH intermediate, and how the changing energy barriers between the different intermediates have changed. And clearly, this energy will be higher for CO and CC breaking than for the dehydrogenation steps. So then we characterize these materials. And so you have on top some XRD, which simply shows that we have platinum 111 polycrystalline phase cubic center, and the despacing decreases with increasing the amount of nickel as expected, which means that platinum and nickel are indeed alloy. XPS shows that you have indeed less platinum and more nickel on the surface as you increase the amount of nickel. And probably you can't see these fancy TMs here, but you could see this, that you have a almost 1-to-1 platinum to nickel in this platinum nickel 2 material. To confirm this, we also went and did EXAFs, and pretty much we confirm indeed that there is a bimetallic product forming because they have a smaller Y-line magnitude in all this bimetallic platinum nickel. We could see that if here we plotted the coordination number for platinum and the nickel, and this is the bond length of different bonds. And we could see the platinum coordination number decreases with increasing the nickel, so less rich local areas. And we could see that the platinum nickel coordination number in platinum nickel 2 is the highest, which means that we have really 1-to-1 platinum to nickel coordination. And then if we go from platinum nickel 1 to 3, there's an increase in nickel oxidation state. So the more nickel we have, the more prone is to oxidation and formation of nickel oxygen bonds, which makes sense. Now, I promise I won't show CVs, but unfortunately I have to. So what I want to show here is, well, this is cyclic voltammetry. How many electrochemists in the audience? So basically here, you basically swap, you set the potential and you swap the potential of your working electrode back and forth, and then you plot the current versus the potential. And so you get peaks, and these peaks means oxidation or reduction. So you see here that we have a clear forward peak for glycerol oxidation around 0.82 volts. And then from this, you could determine the mass activity. So you could see here, this is the mass activity. You see the mass activity is highest for this platinum nickel 2, where you have 1-to-1 platinum to nickel. You could also do a technique to determine the electrochemical surface area of this catalyst by CO stripping. So you absorb a monolayer of CO, this gets oxidized to CO2. And so that means that this is done by the active platinum. And you can determine this, and then you could normalize the mass activity by the specific surface area to get the specific activity. And it seems that this catalyst seems to be very promising here. Okay, maybe I should skip. This is just some stability. This is called chronoamperometry, where you have a potential. In this case, you keep a constant potential and you change the current, you would see how stable your catalyst is. And we could see platinum is stable, but equally stable is the platinum nickel 2, the one that has 1-to-1 platinum to nickel. And we could see that if we compare the potential at which we activate glycerol, for us is very low compared to the literature. You know, have the highest activity similar to platinum, but is very low. Now we wanted to gain insights into the mechanism. So I told you about CO stripping and how it works. We did this for all the catalysts, pure platinum, and then all the 3 of them. And again, I think our focus should be on this because it seems to be working a lot. So what we did, we cycled the catalyst in KOH between 1 and 10 cycles. And we did that to activate the surface. Of course, if you cycle your catalyst with nickel on the surface, under this condition, you'll oxidize the nickel, and you form nickel oxyhydroxide, nickel OH, how is that called? Nickel, oh, I always mix it up. Oxyhydroxide. So on the surface. And so you see that all these 3 bimetallic, they have 2 reductive peaks. Platinum has 1. And so that says that maybe there is this bifunctional mechanism here. what you could see also the platinum nickel 2 has the highest current if you integrate this into, and so it seems that it has a promoting effect. Now, we did this to understand how CO would absorb and how we would oxide on this highly oxidized surface. And then we did the same with glycerol. And finally, when we did this with glycerol, what you could see here is the same experiment when absorb glycerol on platinum. And this is the platinum with excess of nickel, 1-to-1, and very little nickel. You see that you could see oxidation stripping peaks. You see that the adsorption is very slow, so we know that the kinetics of the adsorbates are quite sluggish here. But again, you see that this exhibits the highest peak area among all the catalysts. And you could see that there is just one single peak compared to the CO stripping, which means that when we adsorb glycerol, probably we don't have a bimetallic mechanism. Now we went and did some inoperandoxanes, both at diamond and ECRF. And this is our cell where we have our platinum nickel on carbon paper, our working electrode, and we have our reference and counter electrode, and we could do this in operando. And again, we did this in the absence of glycerol, and we could see that the same spectra changes quite a lot. We suggest that the nickel is indeed oxidized. And we combine this nicely with spectroelectrochemistry in collaboration with James Duran in my department, and we really see the nickel hydroxide transition to this nickel oxy hydroxide, and especially at higher potentials. But when we work in the presence of glycerol, we actually saw no change anymore. So that means the glycerol is really blocking the nickel surface from being oxidized. And so you don't have the bimetallic mechanism, you just have nickel changing the electronic structure. It's very nice to see the nice match between science and spectroelectrochemistry, where you see no change in the oxidation state here, which is quite nice. And we also did some FTIR, but there's a bit too much to show. Now, what are we making on this? So it seems this works the best. So we look at platinum nickel 2, and it seems that we actually make C-free products, which is this glycerate and tartanate, a low potential, and then we have CC cleavages, a higher potential to make glycolate and oxalate, which you can't determine by HPLC, but we've seen it by FTIR, and you could see how the glycerol concentration is going down. So if we look at all these catalysts, what we see is that we always make this mixture of products, that we always make more C-free products at low potential and more C2 products at higher potential. And the more nickel that we have on the catalyst, the more CC cleavage we have. So nickel promotes this CC cleavage of the bonds, and the Faradaic efficiency, which is mole of product with electron transfer versus total charge, is changing depending on the potential. This pretty much says the same thing, and I just want to summarize this here, that basically in alkaline conditions, clearly nickel on the surface will form nickel hydroxide ions, and they will bond strongly with glycerol molecules, and they will block further oxidation and further OH absorption. So nickel modulates the electronic structure, and it will really affect how these intermediates are binding. There is no bifunctional mechanism here. And as I said, compared to pure platinum, where there is a lot of CO poisoning, here there's less CO poisoning, particular for this platinum nickel 2, which has a very high poisoning tolerance and also has the best selectivity towards the product that we want. So pretty much in picture means that here at low potential, you have low CC binding, energy increase, you have high CC binding, and this seems to be optimal. And just very briefly, and I can't give details about this, well, we made this mixture of acids from glycerol. We understood the mechanism was interesting, but then we were wondering, should we actually target something? What do we want to make from glycerol that is useful? So this is the market size for glycerol derivatives. And in fact, Hui Luo, my postdoc, went to a tech accelerate program at Imperial, and she was advised that if we could make lactic acid from glycerol, we would be in business, and that would be an amazing commercial opportunity. So then we were thinking, how can we make lactic acid from glycerol? And so, of course, you all know the lactic acid is normally done from glucose by fermentation. You could also do fermentation to get this hydroxyacetone, and then you could do thermocatalysis. And so we were thinking, can we do this via electrocatalysis? And does that even make sense? Well, you would produce hydrogen on the other side. And I haven't talked about the hydrogen side because that's always, but can we make lactic acid with high selectivity? And we found this paper from Paul Anastas, which is a life cycle assessment paper, which said that in principle, if we could make lactic acid by electrolysis, in terms of environmental impact, is much better than doing the fermentation. So we thought, okay, maybe then let's try to do it. And so, of course, I just show you the electrocatalytic path, which is just what I just showed you on platinum nickel. But then if we could actually get glycerol to form glyceraldehyde, and this glyceraldehyde to form this hydroxyacrylaldehyde that will tautomerize to pyruvaldehyde in a base, then we could actually form lactic acid. So we thought, let's have a combination of electrocatalysis in the first step with something that we got inspiration from heterogeneous catalysis, where it said that this reaction here, this hydroxyacetide to pyruvaldehyde, is catalyzed by Lewis acid groups, and then we leave it in solution because we work in alkaline to make lactic acid. And so I can't give you too many details on this because we're actually trying to protect it. Can't tell you what catalyst to use or what groups, but I think it's easy to figure out. And anyway, the patent is almost filled. But basically, we put platinum on something that has a lot of Lewis acids group, and indeed, platinum does this step, and in combination with platinum Lewis acid groups to this step, and then in solution, you get to lactic acid. And we got very nice results from this in the sense that we got the highest selectivity for an electrocatalysis process to lactic acid from glycerol in the literature. And of course, the hydrogen evolution is happening very happy with much higher efficiency overall because the lactic acid happens at low potentials. And so now, inspired from this, we are also working on PET recycling. So what we do here is we take PET and we put it through a sonochemical process, mechanodepolymerization. And in fact, we are making with really high selectivity bacteriophthalic acid, which is the monomer to make PET, and we're making ethylene glycol. Now, ethylene glycol is a very similar molecule to glycerol. So we are also putting this through an electrolyzer now to produce green hydrogen. And we're very early stage, but we've managed to make ethylene from this. So this is a way of turning plastic waste back into its monomer, ethylene, and hydrogen with some mechanochemistry and some electrochemistry. And so this is quite exciting. We have, again, we are very, very much at the start. So far, we've been only using these Starbucks cups from the coffee, and we've also used Evian. And actually, it's quite impressive that everything gives you 95% terephthalic acid back, and ethylene glycol that I said we're putting through an electrolyzer inspired by the glycerol electrooxidation. So pretty much we're doing from waste to green hydrogen with electricity, and that's something that I'm very excited about. And also doing other biomass reactions, in particular, the reduction of furfural to hydrofurin. That's something that we're also doing electrochemically. We're looking at this molecular phthalocyanine catalyst at the moment supported on graphene or my hydrothermal carbons. And it seems that it's working, and it seems we have also DFT proof that this could work quite nice for this. And so this molecule in principle, if you could open it and hydrogenate it, you could make a jet fuel precursor. And there's many, many other opportunities. So with this, I hope I could convince you that it's actually quite exciting to do catalysis with electrons as well, not only with heat and pressure. And it can give you a lot of opportunities, a lot of fundamental science, maybe real life application. And there's a lot of room for improvement and new and exciting discovery. And it's all done room temperature and no pressure, just with some electricity, which is not the cheapest at the moment, but you know, hopefully things will change. And with this, I'd like to thank my group. And I also want to highlight that, yeah, if you do have female PIs, it is true what they say, you can attract a lot of really talented females in your group. And I hope to see, you know, more women in the Catalysis Hub, hopefully in the future. Thank you very much.
Thank you, Magda, very much. A very interesting talk. Questions?
Yeah. Great talk. Is hydrogen production from biomass electrolysis, is that actually in operation now?
Via pyrolysis and gasification.
Not you haven't got biomass electrolysis working?
No, I don't think it's very, very low TRL level. I'm not aware of anyone doing this at scale. And in fact, of course, you can't really upscale this at terawatts level, but I think depending on the application for chemical industry, you know, if you do it in industry, you combine chemical production with some hydrogen that you use for other things on site, that could be quite viable. We're doing some calculations on, you know, the potential of upscale of this technology at the moment with chemical engineers in my department.
Yeah, I've always thought that the trouble is with electrolysis, you're making all that oxygen that we don't really need. And it would be useful to change that.
Yeah, exactly. Yeah, that was my view. I forgot to say the oxygen is useless. Yeah, I mean, some people will argue otherwise. Quite vital and useless at the same time.
Right.
Fascinating. I think that the work on glycerol, there's an awful lot of catalysis on glycerol oxidation, on thermal catalysis.
Yes.
I agree, there's not so much on electric catalysis. There is some. On thermal catalysis, people are like a broken record on this, I suppose. Gold is extremely good catalyst. Okay. Platinum was reported to be really selective. Papers by Galizo. It turns out they weren't analyzing for CO2, and it's a very non-selective catalyst. So thermochemically, platinum makes probably 95% CO2 under these types of conditions. So, do you see a lot of CO2? And have you tried? Because I imagine you can drive it in a different way.
So yeah, that's a very good question. So as I said, we did in operando FTIR, which I haven't shown because there's already quite a lot, 1 million of pics. So I thought I would show that. But we do see very small traces of CO when we have the platinum nickel free. So we don't see that on I mean, the pure platinum gets poisoned quite easily. But then on platinum nickel free, you have some CO. It's the only catalyst. We see some oxalic acid and some CO there because it really helps cleavage to CC bonding.
But what about CO2?
CO2, yeah.
No, you said CO. Carbon monoxide and carbon dioxide.
Yeah.
Yeah. Do you see carbon dioxide?
Not that I'm aware in this catalyst. That's something we want to avoid because we want to do.
No, but you need. I think you might need to analyze for it. So, okay.
But
it can be dissolved in water. It can be dissolved in the carbonate.
Yeah, but we have done quite a lot of selectivity, carbon mass balance, and all of this, and we just don't really see any CO. We see that with the products that we have, we get to almost 100%.
Okay.
But I'm not denying there might be some CO2, but very little. I agree there's a lot on thermal catalysis, and there's also a lot in electrocatalysis, in fact. But it would be nice, I think with the lactic acid, this is quite exciting, at least for me. That you target something rather than just do it randomly.
Fine. I wonder if with the glycerol oxidation, you've run into an acid which might be more compatible with PEM electrolytes.
Yeah, I mean, we tried initially both in alkaline and acid, and we had really, really terrible results in acid. So we thought that we'll go first with the alkaline one, but ideally you would want to have this in neutral condition. The problem being that you form all this mixture of acids, you never form a pure one. So you actually get the salt version of them, which in a water, which is quite difficult to separate.
I guess with acid, I guess it's just really compatible with PEM electrolytes.
Yeah.
Essentially saying, arguing that you want to replace the original electrode with biomass that used to come. You might still want to run your electrolytes for hydrogen. So
yeah, I mean the hydrogen evolution happens much easier in acid than in alkaline, but yeah, I think for now I think we'll just stay with alkaline for this because we had really bad results in acids to start with.
Thank you very much for your questions. Can we thank Magda Titirici?